Welcome to the team. I am so incredibly pumped to have you all here. Look, in today's explainer, we're going to bridge that absolutely crucial gap between your wild, incredible architectural visions and the literal nuts and bolts structural engineering required to keep a super tall building standing safely. As a lead structural engineer, I want to take you, our newest junior architects, behind the curtain. I want to show you exactly how we make your soaring skyscrapers a safe physical reality. All right, let's just dive right into it. So here is the ultimate question we face on every single major project. How on earth do we build structures nearly a kilometer high without them just bending to the wind? You see, gravity is always pulling your design straight down, sure, but our biggest, most unpredictable, invisible antagonist is actually the wind pushing them sideways. And that dynamic, ever-shifting force, that's the problem we're going to solve together. Here's the thing you have to internalize. In super tall structures, lateral wind pressure is actually a way bigger threat than the actual weight of the building itself. When wind slams into a massive flat facade, it doesn't just push against it, it separates. It creates these alternating vortices of low pressure, a crazy phenomenon we call vortex shedding. This causes complex, wobbling motions and vibrations that, if we don't manage them properly, can literally cause seasickness 80 floors up. And yeah, nobody wants a seasick penthouse owner. Take a look at this equation. This is the hard physical reality we are bound by. The design wind pressure, that's P, equals 0.6 times the wind velocity squared. Now, the real kicker here is that little squared symbol. It tells us that wind pressure increases exponentially with wind velocity. And since wind speeds naturally ramp up the higher into the atmosphere you go, it means the taller you design, the more violently the wind fights back. We aren't dealing with a simple linear increase in force here. We are dealing with an exponential one. Okay, moving into section 1, internal skeletons and modern structural systems. To give your bold designs an actual backbone, we used to rely entirely on rigid frame systems. Think of them as basically grids of beams and columns. But if you look at the rigid frame setup, they completely max out at moderate heights because they're just too vulnerable to bending under those heavy lateral wind loads. But then, the paradigm completely shifted in the 1960s thanks to an engineer named Fezler Khan. He introduced the tube system. By moving closely spaced, interconnected columns to the very exterior of the building, the whole perimeter suddenly acts as a giant, hollow, three-dimensional cantilever. It handles wind forces from literally any direction with incredible efficiency. And honestly, this right here illustrates exactly why engineering matters to you as architects. Because the bundled tube system, like the one they famously used in the Willis Tower, is so insanely efficient at managing the wind, it completely liberated architecture. Just like the quote says, buildings no longer needed to be rigid, boring boxes. This structural breakthrough is the exact thing that allows you to design the true soaring sculptures we see lighting up modern city skylines today.
All right, section 2, sculpting the wind with aerodynamic design modifications.
We can't just rely on the internal skeleton, though. The actual exterior shape of your design is our absolute best defense, and tweaking the aerodynamics is usually the most cost-effective way to slash that dangerous wind pressure. Take a good look at the Burj Khalifa here. That wasn't just a purely aesthetic choice, it's a brilliant piece of aerodynamic engineering. Its Y-shaped footprint has a buttressed core, providing immense stiffness. But more importantly, check out those strategic stepped terraces as the tower rises. Those varying widths naturally disrupt organized vortex shedding patterns. Basically, the wind can never establish a unified rhythmic push against the building, drastically minimizing its sway. And if you incorporate twisting or rotating forms into your concepts, kind of like the Shanghai Tower, you are actively breaking up the coherence of the wind flow. You're essentially confusing the wind with a constantly changing profile at every single floor. This is a massive game changer for reducing those dangerous vortex-induced vibrations and lowering overall wind exposure. So, when you are back at your desks sketching out your initial concepts, I really want you to keep this aerodynamic toolkit in mind. Tapering the profile at higher levels, that cuts down the surface area right where wind velocities are the absolute highest. Softening sharp corners by rounding or chamfering them smooths out the airflow. Adding setbacks, or even doing something wild like adding structural porosity, sky voids that literally let the wind blow right through the building, will drastically cut down the lateral loads that my team and I have to engineer for later. Which brings us to section 3, digital testing and computational fluid dynamics, or CFD. Now, you're probably wondering, how do we actually know if your aerodynamic shapes are going to work? Well, way before we ever pour a single yard of concrete, we test your architectural shapes digitally.
CFD is a total game changer for how we collaborate. It solves these incredibly complex Navier-Stokes fluid flow equations to simulate exactly how air is going to move around your building. The real beauty of CFD is the speed. We can rapidly test multiple variations of your concept, visualize the 3D airflow, spot turbulent hotspots, and predict pressure zones super early in the process. We get to optimize the aerodynamics long before we spend a dime building a physical model.
But eventually, we need the real thing. Section 4. Physical proof via boundary layer wind tunnels. Because catastrophic failure on a super tall scale is absolutely not an option, we always validate those digital models in a physical lab. And that means boundary layer wind tunnel testing. We build these hyper-precise miniature replicas of your designs, usually at a 1 to 300 or 1 to 500 scale. They basically look like incredibly expensive architectural toys. We place them in a massive wind tunnel, complete with a tiny scaled version of the surrounding city to account for wind bouncing off neighboring buildings. Then we blast it with controlled winds. We use hundreds of microscopic sensors to measure the exact lift, drag, and pressure the real building will endure in, say, a typhoon. It tells us exactly where we need to beef up the structural frame. Ultimately, this whole journey, from integrating Fazler-Khan's tube skeletons to your brilliant aerodynamic shaping, right through the CFD and physical wind tunnel testing, it's all about validation. It's about taking your incredible aesthetic vision and merging it with rigorous structural resilience. We're a team, and our goal is to ensure that the monumental structures we build together are going to stand safely for generations. Look, we already know how to beat the wind at 800 meters. But as building materials continue to evolve, getting lighter and significantly stronger, the sky is quite literally the limit. So as you head back to your drafting tables today, I want you to chew on this. With the wind acting as our ultimate, ever-present antagonist, how will your next aerodynamic design safely push us past the 1 kilometer threshold? I seriously cannot wait to see what you all come up with. Let's get to work.